Okay, let's get started now. We're going to talk about just kind of a general overview of all the features of the Midnite Power inverters and batteries today. What some of those specialized features are and how to use some of those things. You go over just basic capabilities of the all-in-one inverter, the smart loads and various ways we can use them, different work modes of the inverter and how we program those differently for different applications, grid, off-grid, things like that, and go over the time-based control features. And then we'll talk a little bit about the PowerFlo 16 and PowerFlo 5 batteries. Inverter capabilities, the 10 kilowatt continuous output, 120, 240 split phase output, or you can use 3 of them to do 120, 208 3-phase, with each of them picking up 2 of the phases and 3 of them creating the full 3-phase. We're rated for up to 3,000 meter elevation and 45 C operating temperature, ambient temperature. So it's pretty conservative in cooler temperatures and lower elevations sometimes. 11.4 kilowatts when we've got solar and battery. The 10 kilowatt is on battery alone. So for battery backup design and off-grid design, that's kind of the realistic number, assuming you may be operating at nighttime. 20 kilowatt surge for 1 second. And this is something that's a lot different than a lot of the all-in-ones. We can do a 13 kilowatt surge at 120 volts on just one leg. A lot of the all-in-ones, that's been a serious drawback, that they just can't handle imbalanced surge loads or heavy imbalanced loads at all. Like a 2 kilowatt air compressor killing a 6 kilowatt all-in-one just because it's on just one leg. So our inverter is one of the few that can actually do good surge capacity with imbalanced loads. 100 amp transfer switch capability. We talked a bit last week about how doing whole house backup of 200 amp panels is not a great idea for a number of reasons. And that's one reason why we didn't opt to put a 200 amp transfer switch built into the inverter. If you want 200 amp transfer switch capability, you can do 2 of these inverters stacked, and then you got 100 amps through each one. Or you can do some of the other things we talked about last week. But natively, we support a 100 amp transfer switch. And like I mentioned, you can stack multiple inverters for higher power in split phase, or up to 3 inverters for higher power in 3-phase. Currently, we can't do more than 3 inverters in 3-phase. That may be in the future, but right now it's 3 inverters for 3-phase. Or you can do, I think we've done up to 6 inverters for split phase, and should be able to do up to 9 for split phase. We've got ones actually in operation with up to 6. Solar input, we've got 3 MPPTs, and each of them has 90 volts to 600 volt input range. One of them's higher amperage, 30 amps usable current. The other 2 are 22 amps. And for IMAX, that's defined as 1.25 times our ISC rated of the array. We've got 40 amps, 30 amps, and 30 amps. We want to make sure we don't exceed that maximum current there. And typically it's only an issue when you're using some of the larger bifacial panels. You'll find that you can only do 1 string per input. Or if you use even old arrays that are configured for lower voltage, higher amperage. On the input voltage, it'll operate down to 90 volts, but it's really best to keep it above about 120 to 130 volts input. It's a bit more efficiency, and also you just don't get a lot of wattage with a 30 amp or a 22 amp input at those low voltage levels. So if you're reusing old arrays that were configured for 150 volt charge controllers, you'll probably want to reconfigure it for a bit higher voltage than that. Even though you could technically just put it straight in there, it's not going to perform as well as if you reconfigure the strings. We have 3 smart load outputs. Two of these can be outputs or inputs. The 60 amp is either a smart load output or a generator input. The 50 amp can be either a smart load output or our AC coupled PV array input. And then we also have a 30 amp smart load. So depending on your needs, you could have up to 3 smart loads or be using a generator and AC coupled PV array, plus still have a smart load left. All of these amperage ratings, both the 100 amp pass through and the 60 amp, 50 amp, and 30 amp on the smart loads are continuous ratings. They're not like typical AC breakers where you're looking at 80% of the amperage rating for continuous use. These breakers are all continuous rated. Smart load 1, our generator input, that has AGS control. We can start and stop the generator based on state of charge. If you're in open loop on voltage mode, say with a lead acid battery or a different lithium battery that's not communicating with the inverter, then you'll have voltage base for your AGS control. Smart load 2, if you set that up for AC coupled PV array, then it can independently control that PV array, unlike if you just put it on the AC output of the inverter. Really works a lot better if it can independently control that PV array when it's AC coupled. It can measure how much power is coming in, and it'll turn on and off that AC coupled array as necessary. You can use it off grid and it'll turn the array on and off. It will also do frequency shifting for control of the AC coupled PV array if it's off grid. Obviously, if it's connected to the grid, it can't do frequency shifting because its frequency is determined by the connection to the grid. We're going to go through some examples of what you can do with these smart loads, because this seems to be kind of a feature that a lot of people are trying to figure out what exactly can I do with them and why do I need 3 of them. One thing, kind of probably the first thing that comes to mind, is dropping less important loads if our batteries are getting low. If we're grid tied and we've got a longer term outage, maybe we segregate our backed up loads into 2 backup panels, one of them on the AC out and one of them on one of our smart loads. And those less important ones on the smart load, we can set to turn off at, say, 60%. You can pick whichever value you think is appropriate. But as our batteries are discharging, to begin with, we're running all the loads. But if we hit 60%, we're thinking, well, we want to save that energy for some of our more important stuff and not just waste it on some big things that we don't really need. So we could have, for short outages, all the loads stay on, but if we've got a longer outage and the batteries start draining, we can dump off a bunch of those loads on the smart load, reserving them. We could actually stage multiple backed up loads panels with different set points and say, these loads, we're only going to run if it's above 90%, which means we're real short outage or we've got good sun. Then have another one drop off at 70% and maybe another one at 40%, leaving the last bit just for the most important things. You could also do this same kind of operation scheme in an off-grid setup where you have different loads staged according to importance and keep just your most important ones on your AC out and put your other ones progressively on different smart load outputs. In off-grid, I prefer kind of doing manual control and thinking about which loads I'm using and how my battery state of charge is doing. But a lot of customers don't really pay attention to that as much as they could. And this kind of gives a way to automatically dump some of the big loads that they shouldn't be running if they're really running low on power, and restricting it just to the most important loads. Another way we can use the smart loads is we can kind of simulate a dump load when we've got excess solar energy. Um, Maybe we've got an off-grid situation, or we might have a grid-tied situation, but we don't have sellback, or we've got a really low payment for sellback. So we really would rather just use that extra solar energy on site when it's being generated rather than selling it to the grid. In either case, we can put some of these dump loads, say an EV charger, irrigation pumps, have them come on at 98% and then back off at 95%. This turns them on when the batteries get near full, and then as long as the solar is supporting that load, they'll just stay on. But as soon as the solar is unable to support that load and it starts pulling the battery state of charge down, it disconnects. We want to put a little bit of room in between those two set points, just because we don't want things turning on and off too rapidly. And also, we usually don't want to wait all the way to 100% to come on, because there can be quite a delay between 98% and 100%, as it kind of does its very slow finish charge and recalibrates the BMS. So 98% will kick it on quite a bit sooner usually. And at that point, we really don't need much solar to be doing that top off of the batteries. So we might as well start dumping it into some of these dump loads. We can directly power the load off the smart load, or we can run that smart load into take one leg of the smart load and use it to power the 120-volt coil of a relay, and then we can use that relay to connect to other things. For example, we can connect into a thermostat system, and maybe when we've got excess solar, we turn our air conditioner higher, up to, maybe we drop it down to 65 degrees and really overcool that space because we've got extra solar, and we'd rather do that than dumping that solar and then having to draw from the batteries later in the evening. We could also do a heat pump, same thing, dump extra solar into the heat pump, maybe bring the space up to 75 degrees instead of 60 something when we've got that extra solar. And then later in the evening, we can kind of coast a little longer because we've heated the space up a little more. In those cases, you don't really want to be just turning power on and off to the air conditioner or the heat pump, but using this interface relay to get into the thermostat system of it and turn it on and off that way can be a better option. Another thing you can do with a smart load is simulate an AGS for a second generator. If we've got a big off-grid system, we might have two generators, one of them going into the generator input and one going into the AC in, where we would normally have the grid connected. The AGS function only works with the generator connected to the gen in, the smart load 1. So what we can do is take one of our other smart loads and use it to power the coil on a relay, and then we've got a normally closed contact on that relay that controls the 2-wire start for the generator. So essentially, we can have the settings for our smart load control when that second generator turns on and off, and we can even pick, say, different turn on and turn off settings for the two generators, so that if one fails to start and it passes the start setting for that one and keeps dropping, then maybe we catch it on the second one. So we can kind of have some redundancy there. And that's a way to use that other smart load, not really to control a load, but to do something else that we want to change based on battery state of charge. We also have all these extra circuit breakers in there, those 4 more circuit breakers to the left of the smart load. And a lot of people have said, what do I do with these? Well, there's a lot of possibilities. Um, Often, if we're doing a separate power shed, we have power needs in there, such as our lighting, our generator, battery charger. And if we're sending a 100 amp feed over to the other building that's the main house, we may not want to put in a sub panel in the power shed and deal with pulling off that 100 amp feed. Might be easier to just power some of those circuits directly off those auxiliary breakers. I've seen what this done on people who are putting in an off-grid house, and they build the shop and the powerhouse first, and eventually they're going to run a feeder over to the main house that can connect into the AC out breaker. But we may be able to feed the small shop just off of a couple of the smart loads. Put a 240 volt well pump on one of the smart loads and some of our 120 volt circuits on those 4 extra breakers. And we may be able to avoid needing a sub panel in that shop completely by just using those extra breakers in the inverter. Functional modes. This is kind of a big confusion point for grid connected systems, especially. Off grid, that kind of makes sense. We use it for off grid systems. There are also some grid connected systems where you'll want to choose off grid, specifically if you're not getting an interconnection agreement with the utility. You don't want to operate in parallel with them, but you want to operate off your solar most of the time. And you can connect the grid to the generator in and use the AGS controls to control when the system uses the grid. This, by not operating in parallel with it, it keeps you from having the possibility of accidentally exporting power back to the grid. Even in zero export, if you don't have all the settings right, specifically always drawing a little bit from the grid to take into account the little blips when load changes, and it might take a second or two for the inverter to respond to that change in the load, and you might sell power to the grid for a second or two. The more advanced utility meters can tell that, and you will get in trouble with the utility. By operating in off-grid mode with the grid just basically pretending to be a generator, it works a little more safe doing that. Legally, if you're going to operate in parallel with the grid, you need an interconnection agreement, even if you're not selling to the grid. For self-consumption, this is usually the best one for most grid-tied setups, even if you're not really wanting to use the batteries. And we'll talk a bit more about this on the next slide. Grid feed and priority. This is really just for batteryless grid tie systems. If you're wanting to add batteries later and you're using one of our inverters just basically as a straight grid tie inverter with no batteries, with the intent to add batteries later. You can also use it for grid tie systems with batteries, but it's got some issues that I feel are better solved by setting it for self-consumption and programming that. Self-consumption, what it tries to do is use the batteries and the solar to power the load whenever it can, rather than using the grid. So anytime that the batteries are above state of charge set points you've set, it's allowable to use from the batteries, or that there's extra solar, it's going to use that to power the load. The ways that we can adjust that is by knowing what overrides self-consumption. There's basically three main things that will override this self-consumption mode and say, stop using the batteries to power the load, use the grid instead. One is if the battery drops below the reserve capacity we've set. So we might say, I want to do self-consumption and operate my loads from the grid, but only down to 50% on the battery because I want to keep some in my battery in case I have a power outage. So we set that reserve capacity, and then once it reaches there, it'll switch back to powering the loads from the grid. That overrides the self-consumption mode. Another way to override it is to set a charge or discharge time period. This we'll talk about a bit more when we talk about the time periods, but essentially, anytime we have a charge or discharge time period, this overrides self-consumption, and instead, it will charge at the set rate up to the set state of charge, or discharge at a set rate down to a set state of charge. Third way we can override self-consumption is if you select force charge from grid. This is really for when you're doing mostly self-consumption, but say you've got a big storm coming and you suspect the grid might fail. You want to top your batteries off to be ready for a possible power outage. You hit force charge from grid, it'll charge the batteries up from the grid. This overrides self-consumption, and it's also a one-time thing. So once it reaches full charge, that'll toggle back off so it doesn't stay on. So that's something to know about that, is that it's not like a permanent setting. It's like a one-time, let's charge these up to get ready for a power outage. And then once it goes back into normal operation, it's going to go back into whatever you had it set as before. Another thing to realize is that grid export can be enabled or disabled during self-consumption. So a lot of older inverters, if you did a self-consumption setup, which was usually called a high battery transfer or a low battery transfer, depending on the terminology they used, where it would operate from the batteries until they got down to a certain point, you usually could not sell to the grid. Our inverter, you can separately control whether you're selling to the grid. Now it's going to charge your battery up first, but once the battery's full, if you still have extra power, you can say, well, at this point, why not sell it to the grid if you're allowed to? If you have a grid that you're not allowed to, then you could disable grid export and it'll just operate the loads from the battery, recharge the battery from the solar, and then run the loads from the solar once the batteries are full, but throttle down that solar to keep from having any extra exported to the grid. So you've got the choice. You also have the choice of picking what is your grid export level. Say you've got an interconnection that can only handle 4 kilowatts of export, but you've got a 12 kilowatt array. You could do self-consumption and then tell it, you've got extra solar, you can export up to 4 kilowatts, but not any more than that, and it will limit to that. Not all utilities are accepting this ability to limit the export. Some of them just base it off of rating of the inverter or rating of the PV array and don't really look at the ability of the inverter to limit that export, but it does have that ability, and if your utility will accept that, that is one of the settings that is only accessible by the installer levels, not the end user. So that qualifies for requiring a password and everything to change, and it's not accessible for the end user to just be changing that grid export. That's a requirement of some utilities for accepting that. Time-based control. This is usually what we use when we are trying to do time of use setups where we have peak demand times or peak rates during certain times of the day. So we want to change what the inverter does at different times of the day. These override the self-consumption, and what we most commonly do is say we've got a peak rates between 4 p.m. and 8 p.m. What we would do is set it for self-consumption and then set charging times for every time except 4 to 8 p.m. So that overrides the self-consumption and charges the batteries during those times. During 4 to 8 p.m., there's no charging time set. It goes into self-consumption. It discharges the batteries till we get to 8 p.m. or until we hit our minimum reserve SOC on grid. And once we get to 8 p.m., it says, oh, I've got a charging time now. I'm going to charge the batteries. If we have not turned charge from grid on, it doesn't do anything because there's no solar to charge the batteries, but it stops using the batteries to power the load. It'll flip back to grid powering the load. If we've got it set up like this, it'll start charging the next morning when we have a charge time set. If we want to, say, top the batteries off right after the end of peak demand times, what we would do is turn on grid charging for a charging time after 8 p.m. Right now, we're still working on this in the firmware, and it's not in the current version, but we're working on a version where you'll be able to set during this time period, I want to not only charge, but I want to charge from the grid, not just from solar. That would let you immediately top off your batteries after the end of peak demand times rather than waiting for the next day for the sun to come up. So a little more flexibility. Right now, it's not quite as flexible, but that's some of the future features we're working out in new firmware. Discharge times are a little more complicated. Discharge times are to dump the batteries at a certain rate. So you might think, well, wouldn't I do my time of use setup by setting a discharge time from 4 to 8 p.m.? And you could, if you know that you can't meet your whole load and you only want to meet a certain portion. Say you know you've got a 12 kilowatt load during that time, and you want to take 6 kilowatts of it off and leave the rest. You could set a discharge time. But if you know that you might have 12 kilowatts of your load and set it for a 12 kilowatt discharge, obviously that might be a stacked inverter system because it's more than 10 kilowatts of a single inverter. What it's going to do is sell 12 kilowatts continuously for that whole time, regardless of whether the load is that large or not, which means it's going to be selling your batteries to the grid. Now, if that's your intent, this works pretty good. There's some time of use setups where the utility has said, during this time period, here's your rate. And if you sell to the grid during that rate, if you buy, you get charged that much. And if you want to charge your batteries on off-peak later, fine with us. Most utilities haven't done that, but some of them said, don't care what you do with your batteries, here's the rates, and you can decide what to do. In that case, you might say, during this peak time, I just want to drain my batteries, selling it to the grid. If I've got loads at that same time, it'll go into that first, but any excess, I want to go to the grid because I'm getting paid this high amount for selling to the grid. So that's where you might set a discharge time and calculate it out so that you'll drain your batteries as much as you want by the end of that time period. But for general time of use, having self-consumption do it, because that'll just meet the loads rather than selling the batteries to the grid, is usually better. Another situation that we run into is peak demand, where you may pay charges based on the peak kilowatts you draw from the grid, not just the energy use. Not real common on residential setups, but can exist. There, we actually have a completely different tool is where we set our grid input. We can set that, it comes default at 24,000 watts, that's 100 amps grid input. But we could set that much lower. We could say, I never want to draw more than 4,000 watts from the grid, and it will power more than that from the batteries. You have to be careful when using this to reduce your grid input, because if you can never draw more than 4,000 watts from the grid and your average demand over the whole day is more than 4,000 watts, you better have the solar to make up that difference, or else you're going to run your batteries down and have to do an emergency switch back over to the grid. So make sure you've got enough solar if you're doing limited import from the grid, that you're not going to run into a situation where you've run out of power. Another thing our inverter can do is what we call normal loads. And this diagram kind of explains what is that. That was a baffling term when I first saw it, because it's not traditionally used in inverter setups. But here's kind of a diagram that shows we've got backed up loads and we got normal loads. Normal loads being everything that's not backed up by the inverter. It's everything on our main grid panel, not on our kind of separated out backed up loads panel. What it does is we've got CTs on those two lines coming in from the grid, and the inverter can tell how much current is on those lines coming in from the grid. And what it does is it sells just enough power through its AC out to the backed up, or to the backfed breaker in that main panel, to zero out the power used by all those other loads. So it's selling just enough power that there's no power coming in from the grid or going out. And that's what we call support normal loads. So even those loads, they're directly connected to the grid, but they're not drawing power from the grid because we're selling just enough to kind of balance that out. This can be useful if you don't want to back up all your loads, but you do want to be able to use as much solar as possible and batteries rather than exporting to the grid. Maybe you have a zero export system where you're not allowed to sell to the grid, or maybe it's just a really unattractive selling rate. You can essentially use more solar power than just what would go to the backed up loads without just selling it to the grid and buying it back at night. If we have time of use metering, and during those peak times, we don't just want to avoid drawing power from the grid for our backed up loads. We would like to avoid drawing power from the grid for all the loads in the house, even the ones that they're not important enough to be backed up, or maybe they're too large or too energy intensive. But we could zero out them during that peak time period. So that's use of the support normal loads. Some things to know about this is that if we do have zero export required, the utility is not allowing us to export, we need to set the settings such there's always some use from the grid. This is to avoid accidentally selling during sudden load changes, because it's selling a certain amount of power into that main loads panel. We go back here, it's selling a certain amount of power into this main loads panel, and say something big in that main loads panel suddenly turns off. It's going to take a second or so for the inverter to respond to that and reduce the amount that it's selling into that panel. What it'll do is it'll see a spike going back to the utility through those CTs and say, oh, I got to reduce that power level. It does that pretty quick, but not fast enough for some of the new smart meters. And the utility will say, you were selling power, you weren't supposed to. So to avoid that, we usually keep anywhere between, we can set it between 30 watts and 300 watts. In a typical house, I find that usually 100 to 150 watts is enough to prevent sellback, but it really depends on what loads you have and how fast they tend to change and what kind of loads they are. Motor loads can have a bigger effect due to some of the um, inductive effects than resistive loads. But anyway, you're going to have some import from the grid. You're not going to really be supporting quite all of the normal loads if you're trying to do full zero export and make sure you never sell back. Another thing to realize is, of course, these normal loads will lose power during a grid outage. They're on the grid panel, they're on the grid side of that isolation relay in the inverter. The grid goes out, it's going to open that relay and it can't support those normal loads. So it's only when the grid is up that we're doing this. And obviously, if we've got a situation where we've connected the grid to the generator input instead of the grid input because we don't want to inadvertently export to the grid, we can't support normal loads through the gen input. It will never sell power to the generator because that's really bad for generators. So if we're pretending that the grid is just a generator, we can't do the support normal loads. Next week, we're going to have a whole training on these CTs and different options there. There's a lot of details and where you can put them and programming them and how to do it right, because it's very particular to some of the setups there. So we're going to talk all about that next week. Here's a big question that comes up is, how do I set your inverter to just do grid tie battery backup, keep the batteries full, and sell power to the grid when I have extra solar? This is kind of the standard operation for most older inverters. Some of them, it was the only mode of operation. There was no way to really operate from the batteries. It was more like batteries are only for a power outage. And the new all-in-one inverters, it's actually not straightforward to set them for this older, simpler setup. There's two issues going on. One is switching from lead acid to lithium batteries. We don't want to be float charging the batteries all the time. And that's what a lot of these other ones did in kind of just keep the batteries at this voltage, whether it's day or night, and be constantly float charging them. When we switch to lithium, it gets a little more complicated because we don't want to be float charging them. The BMS in the battery in a closed loop system actually tells the inverter what to do, and it keeps it from float charging the batteries. But it introduces a second issue, is that if we're keeping a lithium battery at 100% on the BMS all the time, we have what we call state of charge drift. The inverter at nighttime, it's drawing DC power from that battery to keep its brain and stuff going, even if it's not powering the loads. And if that current draw from the battery is below a certain level, the BMS doesn't see it. Typical BMS, if it's under 1 amp of DC current on, this is not just our batteries, this is pretty much all lithium batteries, the BMSs are not that accurate at low amperage. They're not as accurate as the old amp hour counting meters like a Trimetric or a Victron Smart Shunt. So if they have less than 1 amp of current, they just don't see it. And if you've got one of our inverters and 2 or 3 batteries, each battery sees less than 1 amp of current. So you can be drawing a little bit of power overnight, and none of the BMSs will record that. They'll still say the next morning, I'm still at 100%, when they're really not. They might have gone down to 99 overnight. The next night goes down to 98. You keep that up for 2 or 3 months, all of a sudden you've got a battery that the BMS thinks that it's been kept at 100% because it's never seen a big current come out of it, but it's not. It could be significantly less than 100%. We're working on some firmware for our batteries, which will actually recalibrate at state of charges other than 100%. and correct for this, but for now, this is kind of an endemic issue of just about all lithium batteries out there, that the BMS can drift off from reality when you have very low currents. When you have this grid tie battery backup system, that's precisely the situation you're in, where you've got really low currents just from keeping the inverter itself on at night, and you slowly drift off. So the way to solve that is we put the all-in-one inverter in self-consumption mode and set our reserve capacity down just a little bit below 100%. I usually pick 95, 96%. And what this does is it exercises the battery just a little bit each night without really draining it much. And what this does is in the morning, the BMS says, I'm not at 100% anymore, because it's actually pulled it down at a higher rate by running the loads a little bit until it got down to 96%. And it says, I'm at 96%, I need a top off charge. And it does a top off charge. It goes through its little recalibration when it hits 100%. And it's actually keeps that state of charge drifting from happening by dropping it down and then recharging it each day. So this is why I prefer this rather than setting that reserve capacity to 100%. That would work for a while and it would just keep the batteries completely full, never pulling power off of them. But it can have the state of charge drift from reality due to not seeing those low currents each night. So by setting it down a little bit, it prompts it to actually top it off each day and keeps it better in sync. Moving on from the inverter to our battery, we've got the PF16 wall mount battery. This one's actively balanced and has built-in heaters. So those are kind of the two big differences, other than just being a larger size than our other battery. All of our batteries, there's no programming needed for the communications other than setting the inverter to MidNite battery and plugging the cables into the right spots. There's no dip switches to set or addresses or anything. You can have up to 16 batteries on one inverter bank. And because these are actively balanced, we rate them for 8,000 cycles and give a 15-year prorated warranty. The PF5 rack mount batteries, those are passively balanced, which is like most of the batteries out there nowadays. And that's just not quite as good at balancing all the cells because it only operates when the batteries are just about full, kind of up there in the high 90s to 100%. Whereas the active balancing can do a lot better job at balancing because it's operating at more different points along the state of charge scale. Similar, other than that, we can stack 16 of them, no programming needed, and these have a 10-year warranty and 6,000 cycles. These rack mount ones, we need at least 3 batteries per inverter. The wall mount ones, you can do 1 battery per inverter. Better is to have 2 of the wall mounts per inverter or 4 or 5 of the rack mounts per inverter to really get full, if you're really taxing that inverter at full surge capacity. But we do allow using 3 of the rack mounts and 1 of the wall mounts per inverter. And that's it for the presentation, but we'll look at questions. We got a question on maximum PV array size. So we specify 15 kilowatts of PV array. It's actually a little more complicated than that. You want to definitely stay below those amperage limits because exceeding the amperage can damage the machine. So exceeding that maximum 40, 30, 30 for the imax or 30, 22, 22 for the operating amperage, that can damage the machine. But if you look, say you had a really high voltage array, 30 amps, you can get a lot of watts out of that. So if you were running higher voltage arrays, you can actually put a lot of power, but you're just not going to get that much power into the machine. So that's where you get into over paneling questions of how often do I have sunny days versus cloudy days. But as long as you stay within the voltage limits, obviously never getting above 600 volts open circuit and never getting above that 40 amps short circuit current and 30 amps short circuit current on the other two with the 25% adder. That's to account for edge of cloud effects or stronger than normal irradiation, things like that, that might bump it above the rated ISC. So you can put more PV array on there, but just make sure you don't exceed the amperage limits, and it will clip if you get too much on there. So the PF5, whether you need to fully charge that more often than the PF16 because of the passive versus active balancing, I don't know. What are your thoughts on that, Logan? I would generally think that it probably is more important. However, there's a couple different reasons to get to 100% state of charge regularly. Lithium, we got away from having to get to 100% all the time to prevent sulfation, because that was a big issue with lead acid batteries that we recommended always getting up to 100% once a week. Lithium stopped that, but there's still the balancing issue and the state of charge drifting issue. I would say for the balancing issue, it's probably a little less important to get the PF16s up to 100% regularly. But for the state of charge drifting issue, I would still try to get them up to 100% once every week or two. This is usually off-grid systems in the wintertime where they're just not getting full regularly. I've also seen this state of charge drifting issue on grid tie systems where the settings are such that it never gets up to 100%. And that's just where you want to look at your settings and think, I want to make sure this battery gets to 100% at least once a week, just to make sure my state of charge is being accurately measured and I don't run into a situation where my battery's actually discharged a bit more than my state of charge is indicating. But you don't need as much for the balancing, but for the state of charge drifting, you still need to. So I would say, yes, it's more important for the PF5s, but it's kind of like an additional issue, and it's still important for all lithium batteries to do that regularly, just to keep that BMS in sync with reality. Any other questions? Yeah, I would say once a week is good. Once every week or two at most. Seeing any other questions? I'm gonna wrap this up. Thanks for coming. And next week we will be going over installation of the CTs, talking about the support normal loads and how to use the CTs and where you can put them, and all topics relating to that. We'll see you next week.